Hello, I'm Katie Lean, and I work in the microwave radiances and atmospheric motion vectors at ECMWF. So I've just been working on a study that's been funded by ESA, and in this study we're looking at the optimal design of a future constellation of small satellites carrying microwave sounding instruments. And in this study we're looking at quite a broad range of questions, looking at how the number of satellites, their distribution, and the use of humidity or temperature sounding channels complement each other and their relative benefits. So we're looking at quite big questions here. And then just a month ago we've started quite a complementary project which is funded by EUMETSAT. And here we're looking very focused at the Arctic weather satellite and what the relative benefits of the different constellations they would like to try for the actual constellation to be launched later in this decade. To look at the relative benefits of the constellations, we use a method called the Ensemble of Data Assimilations method, or the EDA method. So the EDA consists of a finite number of cycling assimilation, and we use it already operationally to initialize our ensemble forecasts and also the flow-dependent part of the background error in our deterministic forecasts. When we're looking at the relative benefits of new observations, so the EDA uses real observations, it uses the full observing system, and then on top of this we can add simulated data. And within the EDA, each of the different members are generated by perturbing the observations and the forecast model. So what we're looking at really here is the variation across the members in the ensemble. So if you imagine the members in a trajectory through the assimilation window, when we add observations, it modifies the trajectories of all the different members and hopefully brings the spread of these members closer together. And this is equivalent to reducing the uncertainties in the forecast. So the idea is we add different constellations of these simulated data, and then we can look at the changes in this variation, in this EDA spread. And from that we can see how the uncertainties have been reduced and which constellations are giving us the most benefit. When we're doing this study, in order to find out whether the results are reliable, first of all we look, because we can use real observations, we can do a sort of calibration step. So we can compare the results of EDA spread reductions to looking at traditional assimilation experiments where we would look at the actual forecast error, so comparing the forecast against a reference. So we can look at this relationship with real data. Then in terms of the simulated data, there's also been a study using radio occultation, looking at the assessing different constellations, again using the EDA method. And in this one, we have simulated the radio occultation data that we actually have already. So we can run the real data and the simulated data. And these results have been compared by my colleague Katrin Lonitz, and she has shown that we get very similar results whether we are using either real or simulated data, which gives us a lot of confidence that these spread changes are very realistic. So the EDA method is a very general method. We're using it here to look at constellations of microwave instruments, but we've also used it for radio occultation. It was very first developed at the ECMWF to look at the potential of Aeolus. So really it is very general. We can add any type of constellation, any type of instrument, and mainly the issue then is about how we use the instrument in our system, because we are using it as we would use the real data. But the EDA scheme is very general and can be applied for all sorts of different applications. As we move forward into a complementary study looking at the Arctic weather satellite for EUMETSAT, here the focus is much more on the Arctic area as well as globally. So we will be looking at it more from a global perspective for global NWP, because these constellations will be sampling the Arctic regions and the whole planet. So we will be assessing in a similar way to what we have done for the ESA study, a number of different constellations with a number of different satellites in different orbital planes, and then giving some guidance to EUMETSAT in terms of the relative benefits, and perhaps a little bit of guidance then for them on the cost to benefit of how many satellites they should launch.